Hello, everybody. So, we talked about mutual inductance, and now we're going to talk about self-inductance. So imagine a single coil now, and that single coil has a current running through it and a magnetic field that it generates. Well, if this current I is a function of t, then I have a changing delta phi b over delta t. And that leads me to the idea that the EMF here is going to be equal to N phi b delta phi b over delta t. And that's going to be proportional to delta I over delta t. So when I have a coil that has a changing current, that's going to result in self-inductance because the current in the coil itself changes phi b over phi t. And we're going to define the inductance or self-inductance L as Li equals N phi b or L equals N phi b over I. And that leads us to the EMF generated in my coil is equal to this constant L, the inductance, which is in units of henries, which are enormous units, and then delta I over delta T. So what does that mean? L's are going to be circuit components like we've had capacitors and resistors. So if I is increasing here, so I is increasing, then that means that it's increasing the flux on the coil, which means that my EMF is going to be generated in this direction. So it's going to be generated in the way that reduces the flux that goes through the coil. If I have a decreasing I, so let's say I is decreasing, that's going to try to increase the EMF because now the flux is decreasing. It wants to try to oppose that, so it tries to increase it. So an inductor sort of works in a way that tries to keep it the status quo. So as I ramp up the current, the inductor tries to push it back and goes, no, I'm going to have a bunch of voltage drop across it. And then as I decrease the current, if I try to take the current off really fast, it goes, wait, and pulls and tries to get a EMF that direction. So the EMF is always in the opposite direction as the way the current is trying to change. So if I'm increasing the current, I have a negative EMF, and if I'm decreasing the current, I have a positive EMF. And that is self-inductance. So you can probably guess that we're going to have LR and LC circuits, and those will be coming up in separate videos. All right, so let's take a minute and talk about transformers. One of the most common applications of these ideas are in transformers, and transformers are how we are able to transmit current from a distribution station at very high voltages, which means low current, so we're minimizing our power losses, which are these I squared R losses. And at the power distribution site, we might have voltages of 25 kilovolts all the way up to hundreds of kilovolts. But in the house, we have a 120 volt supply. And when we talk about AC currents, we're not usually saying 120 volts is the maximum voltage, but it's the RMS or root mean square voltage. So it's the maximum voltage or peak voltage would be 120 divided by the square root of 2. or times the square root of 2, rather, sorry. 120 times the square root of 2. So what I can do is I can create two different windings that are electrically isolated from each other, but the flux travels through an iron core, so I don't lose any flux, from one coil to the other coil. And I might have my generated source in red, so this could be my 25 kilovolt source, and the source that goes to your house in black, and that would be the 120 volt source. And the generated source I have over here, this symbol with the squiggly line that says it's an AC generated current. And on the right side, or equipotential or potential source. And on the right side, I have a load, just a resistor. So since the flux is the same going through both of them, I know that I have this relationship that looks like the voltage in the first coil divided by its number of coils is equal to the voltage in the second source divided by its number of coils. Or you might think of it as V2 over V1 equals N2 over N1. So now by changing the number of windings in each of these coils, I can either step up or step down the voltage. All right, thanks guys.